Okay, so the example number 5 is going to be about the blanking, clearance, and the force. So the example says that we have a round disc of 150 millimeter in diameter to be blanked from a strip of 3.2 millimeter, of course, thickness, half hard cold rolled steel, whose shear strength is 310 megapascal. Remind what will be the appropriate punch and the die diameters and the blanking force. So again, we have the analysis of the sheet metal cutting operation. So you can see in the following steps that the part is going to be held by the die and is going to be forced by the punch. You can see that we have the clearance here. Here we have the thickness, that's the velocity, and force is going to be applied when we're going to have the contact. The initial plastic deformation will be happen, the penetration will be generated, which is going to be the gap between the original surface and the new position for the deformed surface, until again to have the fracture to be happen and the part to be released. So that's what we have in the shear cutting operation. The parameters we have here once again going to be clearance C between the punch and the die. We have the stock thickness T and the type of the metal and the strength and the length of the cut. Okay, so the clearance, so let's define these parameters and some of the relationship among them. For example, we start with the clearance, where the clearance C in the shearing operation is going to be the distance between the punch and the die as shown in the figure 20A. The typical clearance in conventional pass working is going to be in the range of 4% and 8% of the sheet metal thickness T. Okay, so it's a percentage. The thicker material you're using, you're going to have more clearance between both. Okay, now we continue and you will find. Okay, so the figure 25 is going to show us what will be the effects of the imperial clearance. The too small clearance will cause the fracture lines to be passed up, and this will be doubling the furnishing and raising the cutting forces. However, the too large clearance will pinches metal and increase the burn. So for a very straight edges, for example, shaving, fine blanking, we need to, you can check the section 21.3 in the book. Clearance is going to be roughly about 1% of the stock thickness. So once again, we just want to explain to you that the narrow clearance is going to make the force too high to do the work, while the large clearance is going to cause the fracture and the burr need to be removed later. So the clearance can be calculated mainly by using the following formula. Of course, this will depend on the sheet metal type and thickness. So you can see that this parameter is now going to be calculated. Now, the clearance is going to be equal to the AC multiplied by the thickness. C, the clearance in millimeters, the AC clearance allowance. T is going to be stock thickness in millimeters. Okay, so that's the thickness we're talking about. That's the clearance we are calculating. The clearance allowance is determined according to the type of the metal. So the table at 21 is going to tell us what will be the metal group and what will be the AC value for each type. So an example here is going to be for the aluminium alloys, and all the timbers is going to be about 0.045. If we're talking about the steel and the aluminium type alloys, 6061, which is the most common one. The brass, all the timbers, and the soft cold rolled steel, soft stainless steel is going to be 0.06. If we talk about the cold rolled steel, half hard, stainless steel, half hard, and the full hard, the value is going to be 0.075. The die opening must always going to be exceeding the punch size, and the clearance is going to be added to the die or subtracted from the punch depending on the whether the punch is going to be a blank or slug. So once again, the blank is going to be the part that's going to be used later for further operations. The slug is going to be the part used in the punching operation to make a hole. So the colored part is going to be simply recycled. So due to the sheared edge geometry, the outer dimensions of the cut part is going to be larger than the hole itself. So for a circular part, this distinction determines which sides receive the clearance is. So in the case of the punch and the die sizes for the round blank of diameter of the DB, they are determined as the blanking punch diameter is going to be equal to the DB, okay, the blank diameter, minus 2 clearance. For the blanking die diameter, it's going to be equal to DB. So that's the die, okay, and that's the punch. So the diameter of the punch is equal to the DB minus 2 clearance. You can see, you can find clearance on each side. For the punch and die sizes for the round hole diameter DH are going to be determined as the hole punch diameter is going to be DH, while the hole die diameter is going to be DH minus 2 clearance. So the other factor is going to be the cutting forces. So the estimates of the cutting force are going to be important because this force will determine what will be the size of the press needed for the operation. The cutting force in the sheet metal working can be determined by the equation that the force is equal to the S multiplied by the T multiplied by the L, where the S is going to be sheet strength of the sheet metal. So the harder the material is, the more force is going to be required. The T is going to be the thickness of the stock in millimeters, and the L is going to be the length of the cutting edge in millimeters. In the blanking, punching, slotting, and similar operation, the L is going to be the perimeter length of the blank hole or hole to be cut. The minor effect of the clearance in determining the value of the L can be simply neglected. So we'll go back to the example. We have a round disc, 150 millimeter diameter. Okay, now we know diameter. Is to be blanked from a strip of 3.2 millimeter, so that the thickness, and that's the diameter dB. Half hard cold rolled steel, so we know the material shear strength is given as 310 megapascal, that they determine the appropriate punch and die diameters, and finally the blanking force. So we start first by having a look to the table. Table 21, we're looking for the material, which is the cold rolled steel, half hard stainless steel, and the half hard and the full hard. So we can find that the value for the AC is going to be equal to 0.075. Now we can apply the equation for the clearance. We know the AC, we know the thickness is 3.2 millimeters. So the clearance is going to be equal to 0.24 millimeters. Next. We continue with that. We found the diameters, so we can, the clearance, so we can calculate the die opening. So the die opening diameter is going to be 150 millimeters, which is the same diameter we have for the round disc. And also for the punch diameter is going to be equal to the dB minus 2c. The c is 0.24, so 2c is going to be 0.48. The dB is 150, and then simply the punch diameter is going to be equal to 149.52 millimeters. Okay, so part B, we need to find the force required to do the work. So we have been given the value for the shear strength. We've been given the value for the T, which is the thickness. We just need to find the value for the L to get the force. So the perimeter of the circle is going to be equal to the pi multiplied by the diameters, and this will be equal to 471.2 millimeters. Apply that to the equation of the force, and we will get that the force required is going to be equal to 467,469 Newton in total. So that's it for this example, and thank you very much for listening.